Okay, so it's a pleasure to have with us this week Persi Diaconis and from Stanford. He's been visiting UBC on some occasions in the past, but this is not really practical now. So we get the next best thing, which is much easier since he's now actually in Portugal here. Persi, please get started.
Ready. Very good. So hello, and it's a pleasure to be back in UBC again. I wish I were actually there, but I'm going to give a talk on stuff I'm working on, and some of the work was done with Kelsey Houston Edwards, who is a recent PhD from Cornell, working with Laurent Saloff-Coste. And I understand that Laurent gave a talk with almost the same title about a year ago, but you'll see we're different. And so the title of the talk, to try to communicate, is Gambler's Rune with Several Gamblers. And what the actual talk is about is the rates of convergence crew. That's me and Laurent and other people who work on rates of convergence of Jonathan and work on rates of convergence of Markov chains. So they're stationary distributions meets absorbing Markov chains. And so for many years, I've been studying how many times you have to shuffle a deck of cards to mix it up. And recently, a few years ago, I realized that not all Markov chains have stationary distributions, of course, and there are absorbing Markov chains. And then if the chain's been going a long while and not absorbed, there's something called a quasi-stationary distribution. I'll define it and come back to it. And then it makes sense to talk about when does the approximation of quasi-stationarity hold, that is rates of convergence to quasi-stationarity. So that's behind this, that's hidden behind this. I should say that I'm in active collaboration talking to Stu Ethier, and I started this subject and worked with Laurent Miklo, and he's in France, and he said he was going to be watching. I don't know if he's actually watching, but it's midnight in France. Anyway, here goes. So just to say it a little bit better, it'll be said better and better, I hope. So suppose I have a finite or countable set, and I have a reversible Markov chain. That is a Markov chain K of xy, a stationary distribution pi of x, and I'm always going to assume everything is connected and aperiodic. Be very careful about that when we write, but let me not do that now. So I have a reversible Markov chain, and I'll use the chain is started at some point little x, and then the chain is capital X1, X2. It's a discrete time chain, and that's in the background. I have a reversible Markov chain on a big space, and then I have a finite set U, which I'll call a domain, and it's just some finite subset. And it should be connected. That is, you should be able to get from any point in U to any other point in U, staying inside of U by the chain. And let tau be the first time that the stochastic process started in U leaves U. That is, it hops outside of U. And there are natural questions that any probabilist would want to answer. How long does it take until we're absorbed? That is, given the start, how long, what's some approximation to the distribution of tau? When we're absorbed, where are we absorbed? So we're absorbed on some kind of a boundary of U, and given that I started at x, where are we likely to be absorbed? So at time of first absorption, where are we likely to be? And I'm looking for approximations. This thing is called a Poisson kernel, P of xy, and or harmonic measure. Anyway, but the final thing is, look at where we're likely to be given that we haven't been absorbed. That is, we started at X, we've run a while, but we haven't been absorbed. Where are we likely to be? What's the distribution of where we are? And it's a theorem that as little t goes to infinity, this number tends to a limit, which is called the quasi-stationary distribution. And you can try to understand what the quasi-stationary distribution is. And if you haven't seen this before, let me just stop the share for a second and just talk to you like a human being. If you haven't seen this before, just consider a path, n points in a row, and we're doing simple random walk, and say we're reflecting at 0 and we're absorbing if we get to n, and I tell you we start at some place, the start place doesn't matter, and we've been running a long time and we haven't been absorbed, then where are we likely to be? And turns out that we're not likely to be near the absorption point. That is, the quasi-stationary distribution in this case is big near the reflecting point, big near 0, and it's some piece of cosine. You can say what it is. If you haven't seen that before, it's interesting, and it's hard to have intuition about quasi-stationary distributions, as you'll see. And so that's one of the things we'll try to develop and talk about. And let's see if I think that's where I was. And let me get back to here. So that's very, very roughly what we're going to be talking about. Except now I have to figure out how to get this thing to move. Okay, the main point of this talk is the following. For nice sets X, I'll define nice in some way, and for nice domains U, and for nice Markov chains, pi and k, we have reasonable answers to these questions, to all of them, and ones I haven't told you about, based on what I'll call the geometry of the ambient space and of the domain. Now, nice will mean, in this talk, something which isn't so familiar in probability language, things that are called John domains and Whitney covers and irregular domains. I'll talk about all of those. And nice Markov chains are going to be what I call Harnack Markov chains. So for most probabilists, at least where I come from, these are all foreign terms, and you see it's better, but I'm not assuming that that makes much sense to any of you, and I'll come and talk more about it. The techniques that we use are the Duke transform, which again I'll explain, something called the cable process, which is basically you take the graph and you think of it as a metric graph with unit intervals between each vertex, and you think of a Brownian motion on those edges. That's then a process. John Walsh used to be around, and he's a great student of things of that sort. I'll call it the cable process, and that's important. And then what I call the geometric theory of Markov chains, which are various versions of Poincaré, Nash, and Sobolev, and parabolic Harnack inequalities. And so for nice Markov chains, using these techniques, we can give reasonable answers. So that's an overview of my talk. Okay, that's where we're headed. And let me do an example. And this is an example, and I'll give motivation for it in a second, but I don't think it needs much motivation. Consider 3 gamblers. Maybe it's Omer, Jonathan, and Diaconis, and one of them has A dollars, and one of them has B dollars, and one of them has C dollars. And then they evolve in the following way. Each time you pick a pair of gamblers uniformly at random, that is, you pick one of the 3 people and you eliminate them, and then the pair of gamblers that's chosen for that round, a fair coin is flipped, and if it comes up heads, Jonathan gives Omer $1. If it comes up tails, Omer gives Jonathan $1. And then you pick another pair of people and you evolve that way. So I hope that's clear, first of all. Now, it's a finite system, and it's all symmetric. So, of course, after a while, one of the three of us will go broke, hit zero, and then you can't gamble if you don't have any money, so you're eliminated. And then the game continues with the other two. But let tau be the first time that one of the three of us is eliminated. That's a random time. And a question is, how is the cash split between the other two, the two remaining people? And how does that split depend on A, B, and C, where we started? Of course, if you start near a boundary, it's different than if you start in the middle. So that's a question, and it's a three-player version of one of the oldest questions in probability, which is the problem of points, the problem that Fermat and Pascal started talking about, namely, as you'll see in a second, this is very connected to the question of, given that we have to abort the game and we have A, B, and C dollars, how should we settle up? What are the odds for each of the three of us? And this is the gambler's rune problem. Of course, since n is, since the sum, the total amount of cash is fixed, you can just look at the amount of money that the first two players have, say x1 and x2, and since I've eliminated people, it's a discrete space, and the space X is the infinite space, but this is X1 and X2. The boundary is, well, if this line is where X1 is 0, so X1 goes broke, this line is where X2 is 0, and this line is where X1 plus X2 is n, namely X3 is 0. N is A plus B plus C. So the gambler's rune problem is you're doing random walk in this domain with these edges, and given that you start here, 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 what's the chance you hit the boundary, and where do you hit it? So I hope that's sensible. There are a bunch of, some things are easy about this problem, and let me remind you of some of the easy, nice things. Classical martingale tricks say, so tau now is the first time one of the three gamblers is eliminated, okay? And the expected value of tau is this nice recipe, 3 times ABC divided by A plus B plus C. So that's a nice formula. Let's try to get a feeling for it for a second. Suppose we each started with $100. We're all in the middle. A plus B, A is equal to B is equal to C is 100. Then it takes around 10,000 steps. That's what this formula says. The 3 cancels out, and so it takes around 10,000 steps. On the other hand, if 2 of us are almost broke, if A and B are 1, and Omer here has most of the cash, $300, then expected absorption time is around 3 from this formula. And you can keep going. Let eta be the stopping time, which is the first time 2 of the gamblers are eliminated. That is the time the game ends. Again, an easy martingale argument says that the expected value of the termination of the game is given by this nice formula, the second elementary symmetric function, and in the units. And when you plug into our 2 examples, how long does the game go on? Well, it's around 30,000 steps. If we're all balanced, then longer than you might think, 600 steps. It's hard to have a feeling for these numbers, at least for me. Another classical, most classical argument says that what's the chance that the first player, the player who started with A, has all the cash when the game ends, and that's proportional to A. It's A over A plus C, and symmetrically. So these are all nice answers, and they make you think, yeah, everything is kind of known. Try to compute the variance, try to compute limits, but still a lot is known. Here's a thing that's not known, and I find interesting. My 3 gamblers, they start with A, B, and C dollars. There's an elimination order. That is, for example, ABC means A is eliminated first, then B is eliminated, and C is left with all the cash. There are 6 elimination orders. Yeah. What are the chances of those 6 elimination orders? Approximations to them, of course. I'd love to have a formula. What are approximations to the chance of these 6 elimination orders as a function of A, B, and C? That's a question that we really don't know how to solve. If you like, you can make it with K gamblers, and I will come back and talk about that. But with 3, we don't know how to solve it. Let me give you some motivation for that problem. It comes from tournament poker, without going into a long discourse on poker. Tournament poker, so the World Series of Poker just finished last week. Around 10,000 players, each anteed up $10,000. So there's a lot of money involved. And then they start playing, you know, seven players per table with many, many tables. And then everybody goes broke except a few people, and then the tables are combined. And at the end, suppose that, you know, there's the final table, and then they're playing, and all of the money is there. So there literally are millions of dollars on the final table. And suppose we're down to 3 players, just for the moment, or 4 players or K players, but let's suppose it's 3 players. And I have I have $100,000, Jonathan has $1 million, and Omer has $4 million, okay? And I now want to know, what are the chances of the given finishing orders? Why is that important? Because whoever winds up with all the cash, they don't get all the cash. They get the first prize of the contest, $1 million. They don't get all the cash, right? They get the first prize. The second player gets whatever, you know, $500,000. The third player gets $250,000, regardless of how much you have in front of you. And so now, if I have to, if in the middle of a hand, if somebody, you know, bets and I have to call the bet, maybe they're tapped out. If I lose, I know how much I'll have. What's my expected value at the end of the game? In order to calculate those numbers, you need to know the probabilities that I just talked about. Is that okay with everybody? We're all grown-ups about probability. Yes, sir.
One question. Could it be a simpler problem to find an individual's expected or placement in the finishing order than to find the permutations themselves probabilities?
It is a simpler problem. We don't know how to do that one either. I'll tell you what we know. It is a simpler problem, and it would be an important problem, but yes, but it seems like a reasonable, natural question, and it really has motivation. Okay, so I not only want to know the chance I finished last, but you're right. You said yes, it is a simpler and reasonable problem. Now you can ask about the model. This problem was suggested to me. I'm teaching a course on the mathematics of gambling Tuesday and Thursday, and I have a guest speaker who's Chris Ferguson, also known as Jesus Ferguson, and he won the World Series of Poker 4 or 5 times. He also has a PhD in computer science, and his dad is Tom Ferguson, who's a wonderful probabilist and statistician. And Chris is a professional poker player, and he wanted to know the answer to this question because it really comes up. And you can't do it by Monte Carlo. I mean, you just can't do it by Monte Carlo. You know, you can do it if there's $100 involved, but you can't do it with big numbers. It's just silly. And you can't, I'll come back and talk about that. Anyway, all I'm trying to do is, I hope the problem has some motivation, and that's a special case of the problem where, I don't want to do that, I want to do this. As I'll tell you, we can do something for 3 players, less for 4 players, not 0, but it's largely open. Even what we can do for 3 players isn't great. It's not bad. I mean, we can do something. I'll tell you all about that. But that's a special case of the problem I'm talking about. And of course, the problem I'm talking about is a very general problem. So yeah, this is a grown-up colloquium. Let me say everything is math now for a while, if I may, stop being friendly. I'm always friendly, but okay. X is a finite or countable set. And pi of x are strictly positive weights. They might not be a probability. They might be, 1 or something, but pi of x are weights on the vertices of my countable set X. I have a general graph structure. I have a set of edges, undirected edges, which I'll, if I need to call them anything. And I'm not going to allow loops right now. And I've got weights on the edges. So that is it's weights on the undirected edges, and they're positive. It's useful to extend the weights to everything and just make them 0 off E. The assumption, a natural assumption, is that the sum of the weights of the edges coming out of X is smaller than pi. That's an assumption I'm going to make. Okay, so that's my setup. And that's a very general setup, right? It's just anything. And then I can make a Markov chain. The chance of going from X to Y is the weight on the edge, mu of xy, divided by pi of x if y is different from x, and what's left for holding if y is equal to x. So this is essentially the most general reversible Markov chain with this structure, if you like. Anyway, that's the setup I'm going to be working in, and there's nothing particularly regular about it. And I've got a process. It starts someplace. I'll start it deterministically at little x, and then it goes x1, x2. I'll work in discrete time. So this setup defines a reversible Markov chain on a set. And, by domain, I always wondered, what do analysts mean by a domain? Well, what we mean by a domain is a finite connected set of X. And connected means you can get from any point in U to any other point in U, staying inside of U by edges in E. Tau, my stopping time, is the first time, and infinity if it doesn't happen, tau is the first time you leave U, and that'll be called tau sub U. And so that's a little more carefully. It's useful to introduce this kernel, the kernel of the Markov chain truncated to U. That's all it is, but let's look at it slowly, try not to rush. So K sub U of xy, it's a sub-Markovian kernel. If X or Y are outside of U, it's 0. And if X and Y are both in U, it's the chance of moving from X to Y. That's a positive operator on L2 of U. U is finite, namely the mapping that takes F into K sub U of F, where K sub U of F is just defined in the usual way, average with respect to this kernel. That's a positive operator and a strictly positive operator, and so connected. And so it admits a Perron eigenvalue, Perron-Frobenius theorem, which I'll be calling beta naught. And it admits an eigenfunction, an eigenvector, and which I'll be calling phi sub 0, phi sub naught of x, and that's strictly positive. That's the Perron-Frobenius theorem. And I'll normalize my eigenfunction so that its average is 1, so over U. So that from U, I have this phi naught, which will be important, and we wish we knew about phi naught. We know some things, but okay. So there's this thing that's called the Doob transform, and let's just define it and say where it comes from. So I'll use the notation. It's a Markov chain on U, and I'll use the notation capital K sub phi naught of xy, and this is the recipe for it. It's my truncated chain, and then normalized in this way. I divide by, well, let's just look. So suppose I sum this in y, right? Well, if I sum this in y, phi sub naught is a right eigenfunction for k, and so if I sum this in y, this will be phi sub naught of x, and that'll cancel that, and with a beta, it's a right eigenfunction with eigenvalue beta, and so I get 1. I hope that's okay with everybody. It's just the it's the Doob transform. It's important that this is reversible with reversing measure phi naught squared, and where this is a density phi with respect to pi restricted to u. Anyway, so this matrix is called the Doob transform. And a classical fact is a classical fact. I can show you all of this. A classical fact, this classical fact is that, look at the right-hand side. For every x and y in u, and for every fixed t, okay, t is 15, look at the chance, given that you started at x, that after t steps you're at y, given that you haven't been absorbed up to, well, this is sorry, and then take the limit as L goes to infinity. So look at the chance of going from x to y in 10 steps, given that you've never been absorbed. Anyway, this limit, it's a little theorem that this limit exists for an ergodic Markov chain. And the classical fact is that this limit is equal to the Doob transform. So the Doob transform, as people know, is the Markov chain restricted to u, conditioned to never leave u. But this is the official definition, and this is a little theorem. Let me give the right-hand side a name. This is a measure. Let nu sub u upper t of y, okay, it's a measure in y, t is fixed, be the probability that the chain is at y, given that it hasn't been absorbed up to time t, and that's the thing we're interested in. Where are you likely to be, given that you haven't died at time t? And a second classical fact, and these are undergraduate exercises, is that the limit, and it's a different thing, the limit as t goes to infinity exists, and it's proportional to the Perron eigenfunction, and this is just the normalizing constant. And I'll write phi naught bar for the normalized eigenfunction, normalized this way to be a probability. And that's called the quasi-stationary distribution. So if you haven't seen it before, it's a little confusing. There are two quasi-stationary distributions. One is, which I don't care so much about, is where's the chain likely to be if I tell you now it's never absorbed. And the second one is where's the chain hasn't been absorbed up to time t. And they're different. I mean, but this is the one we're going to be interested in. So there's this convergence, and now you can ask quantitative questions. Can you say, this is a limit theorem. Can you say for a given domain, in terms of the size of the domain and the geometry of the chain, when does this approximation have any content? That's one of the things that we're going to be talking about. So we're going to study the convergence. The theme of most of the talk is to study the convergence of the chain conditioned not to have been absorbed to its quasi-stationary distribution via the convergence of the Doob transform chain, which is an ergodic Markov chain with an honest stationary distribution. So the Doob transform chain, just an ordinary Markov chain. It's got a stationary distribution. It's not absorbing. We have all the techniques that, coupling, stationary times, eigenvalues, Lyapunov. We have all the techniques that we have to study the Doob transform chain. And what we want to do is transfer that, do the study, but then transfer that information back to the world of quasi-stationarity. So here's a specific theorem which says if you can do one, you can do the other. So here, this is a theorem. This is an elementary theorem. Suppose that my restricted kernel is irreducible and aperiodic, just to not fuss with that. And fix an epsilon between 0 and 1. and fix an x inside of u. So I've got u, and I've got this chain restricted to u. Suppose that for t, that there's an n sub epsilon, such that for t bigger than n sub epsilon, the Duke transform chain is close to its stationary distribution, and this is an L infinity norm. That is the ratio of the chance, x is fixed, the chance of being at y to the stationary distribution of y, take the sup in y, that's less than epsilon. So suppose I know about, I've got a rate of convergence of the Duke chain to its stationary distribution in L infinity. But this is quantitative. Then the conclusion is that the conditional distribution is close to its limit as long as t is bigger than n sub epsilon. These epsilons are the same, and this 1 minus epsilon doesn't change anything. Okay, so I'm going to use that theorem. It's a page to prove it, and there's versions in all kinds of LPs, but this is a clean enough version, and I hope you see what I mean. So this says if you can study the ordinary chain, the Duke transform chain, then you can study the original chain. You can study where you're likely to be. There I am. Now, we have some general theorems, and so these are theorems that say, when can we get reasonable results? What do I mean by nice X and nice U? When can we get reasonable results for the Duke transform chain? Okay, so if you think about it, this is quite general. That is, I've got a general geometry. It's not a lattice. It could be anything. And U, any funny set, could have funny holes, and, it's connected, but it could be a funny set. So I need 3 assumptions, and let me tell you what they are and try to introduce. These are, you study the geometric theory of Markov chains, these are standardish assumptions, but anyway, here they are. So the first assumption is an assumption on the big state space, the set of edges, the weights on the edges, and the weights on the vertices. Okay, and it's the following set of assumptions. The first is that the chain is d-doubling. What that means is that for any ball, if you look at the volume of a ball of radius twice the radius, a ball of radius twice r around x, that's less than or equal to d times the volume of the ball around x. So that's a doubling property, and d is a specific constant, and later I'll say, fix d, and d, you have to determine d. But usually, nice geometry, certainly for our K gamblers problem, the natural measures are d-doubling. Okay. The second thing is elliptic operators. The weights are elliptic, and all that means in English for this setup is the following. There's some constant, which is the ellipticity constant, so that if I is bigger than 1, it's a big constant, it's fixed. If I blow the edge weights up by E, then this edge weight is bigger than pi of x for all x and y. And if you know what the definition of an elliptic operator is, this is the discrete version of it. And so those are, you have to check, but they're natural. There are many, many examples. The third, you have to maybe be on my side of the tennis court, but let me try to make this better for you. We call these local Poincare inequalities, and the Poincare inequality, the usual Poincare inequality, says that the L2 norm is bounded above by a constant times the Dirichlet form, and we need that locally. And so first let me say it and then try to make it look friendlier. Pick a ball for any x and any r, pick a ball around x, and sum over z in that ball, sum f of z minus the average of f over the ball, average with respect to pi, and square that difference. It's like a variance type term, and look at that average. That should be bounded above by a constant. This is the Poincare constant, times r squared, where r is the r of the radius of the ball. And this is like the Dirichlet form, that is the difference between y and z inside the ball, weighted by the weights. And so if you haven't seen that before, it might look funny to you. I don't know how to help that. These are usually easy to prove using path arguments. That is, the way you prove a Poincare inequality is you pick 2 points, y and z, and then you make a path between y and z, and then you write f of y minus f of z is the sum of differences along the path, and then you use Cauchy-Schwarz, and you get this kind of inequality. So it's a familiar thing. We're assuming the availability of a Poincare inequality. In case you look at our paper, and I'll give a reference to the paper at the end of this talk, we allow fractal growth. And I think nobody but Martin Barlow, where you are, cares about that. But unless I'm not attacking anybody. We did the work, but nobody. So this too could be a theta. And okay, but I'm trying to be friendly. I made it a 2. So those are 3 assumptions. That is, my geometry of x is doubling, and the weights are chosen to be elliptic, and there's a Poincare inequality. So that's the first assumption. Okay. The second assumption is a little bit strange. If you haven't seen it, it's absolutely standard in some parts of PDE. Complex geometry was new to me. It's something that Laurent knows about, but I didn't. It's very natural and rich and useful. So it's something to me. So there's a whole world of people that live here, but it's not most of us. So this is an assumption on the domain U, okay? So U is called a John domain, after Fritz John. If there exists a central point, there exists a point 0 in U, and a number R, okay, positive number, such that for every point in U, you can find a path from x to 0, from x to the middle. Here's 0, here's my domain, here's 0, here's x. You can find a path from, a path is just a sequence of points where each edge is an allowed edge in the transition matrix. You can find the path so that the path starts at x, winds up at 0, and as you move along the path, you get further and further away from the boundary. Okay, that's what this says. Let's look at it. Well, first of all, there are 2 conditions. The maximum length of all paths, the diameter of U, if you like, or the twice, 1/2 the diameter. Anyway, the maximum of the length of the path is bounded by R. Okay, that's what R does for a living. And as you go along the path, the distance to the boundary grows. And so we talk about carrots. That is, there's a kind of carrot which starts at X. The point of the carrot is at X, and there it is. There it is. Now, just to, let's see if I think I have a picture of, here, let's try this. No, oh, I don't know. I'm not going to try to do that. Let me not try to do that, but okay. So if that's a strange definition to you, it was strange to me, but there are lots and lots of examples, including, so a metric ball in a graph, any graph, a metric ball in a graph is a John domain. Convex subsets of lattice points in a lattice. Take a lattice in ZD, and take a convex set in RD, take the lattice points inside the convex set, that's a John domain. All natural examples, anything, I mean, you have to work to make a domain that's not a John domain. In particular, K gamblers for any K, they're all John domains. So it would be nice if I could give you an hour's talk on John domains. I'm not going to try to do that. It's a subject, and if you're meeting it for the first time, well, it's good to meet a thing and say somebody's telling you, hey, this is useful. We have lots of examples in the paper. They don't have to be anything like convex. You can take a nice convex set of lattice points and then remove some edges and put in some extra edges and do all kinds of stuff. You can't do everything, but it's a very rich notion. So my assumption will be that U is a John domain. And what that means is that it has a size R, and later R is going to come into the statements of theorems. So the fact that it's a John domain means that there's a diameter for it, which is called R. Okay, that's my second assumption. My third assumption is an assumption on U, the domain, in terms of this Perron eigenfunction. And the assumption is there exists a constant A such that with respect to phi naught as a measure, phi naught is a density with respect to pi on U, this measure phi naught is A doubling on U. Okay, so we said about doubling, the volume of balls is controlled. Twice the ball is A times the volume of a ball. But now the measure changed. The measure is this Perron eigenfunction. And one issue is going to be, unless you know something that I don't, doesn't sound so bad, but it's very hard work to get your hands on phi naught, even in very natural problems. The ones I was waving my hands about, take a convex set in the plane and look at the lattice points inside of it, say something about phi naught. I mean, we can do something, but which I'll tell you about, but it's not free. That's a lot of hard work. That's the Carleson estimates and stuff like that. So there are three assumptions I'm making. The first assumption is on X, and it was that I had an elliptic operator, which satisfied a Poincare inequality. The second assumption was the domain was a John domain. That's my notion of nice. And the third assumption is this assumption on everything, which is A doubling. So that's a lot of assumptions. What do I get from all of those assumptions? Okay, so here's a theorem. Okay. So fix alpha. What's alpha? Alpha is the alpha from John domain. You know, there was an alpha, right? Fix alpha, the ellipticity constant. P is the Poincare constant. D is the doubling constant for the phi naught for the original measure, and A is so fix all of those parameters. Assume 1, 2, and 3, my assumptions. Then I get good rates of convergence of the Doob chain to its stationary distribution, but let's say that better. I need these two facts. We know a lot of other facts, but the Perron eigenfunction, the Perron eigenvalue is like 1 minus 1 over r squared. That is, it's bounded above and below. These are two constants, little c and capital C. 1 minus beta naught is bigger than or equal to little c over r squared, and r is the domain, is the dimension, the r that comes from assumption 3, the John domain. So I have some control over the second eigenfunction of the Doob transform chain, and the L infinity norm, the max over x and y, actually uniformly in x, of the Doob transform chain to its stationary distribution is small if how far you went, if t, the number of steps you take, is bigger than r squared. Here, there are 4 c's in this. The c's are explicit. You don't want to see them. I mean, we wrote them down, but you don't want to see them. They're explicit. They depend on alpha, all the p's and d of a. They don't depend on t, and they don't depend on r. So, so if you want to think about that, our transference theorem says that this rate of convergence also talks about quasi-stationarity. So the the takeaway from this theorem is that the diameter squared steps are necessary and sufficient for convergence to quasi-stationarity. How long does it take the chain to get close to its quasi-stationary distribution, given that it's not absorbed? You have to go something bigger than the diameter squared steps. Okay, now I want to tell you something about this theorem. I'm going to tell you a little bit more about it, of course. So Laurent, Miklo, and I started this subject 7 or 8 years ago in Nice, Toulouse, or someplace.
Persi?
Yes.
Yes,
Question.
sorry. So Jonathan was asking a question in the chat.
Try it.
It is clear. Is it clear that R is proportional to the usual diameter?
Yes. R is the diameter. So R is the R from the definition of John domain. So if you have a triangle, it's the diameter. You know, it's N. You know, but John domains are funny things. You know, they really can have holes and be long and pointy, and so R is the R from the John domain. But if you're in any kind of a reasonable set, yes, it's the diameter of the, you know, if you have lattice points. But technically, and if you're a certain kind of geometer, well, you know, thinking about your domain, you know, your set as lattice points, that's for children. You know, we want to work in general domains. So R is the R from the definition of John domain. Okay, but for nice sets, R is the diameter of the set. Yes. So if you're on the integers from 0 to n, you know, R is n. That's, you know, order n. I mean, here, constants are not being paid particular attention. I hope that helps. But I mean, so there's a technical answer and there's an intuitive answer. But so Laurent, Miklo, and I took the problem I started with. Let me stop this share because it's, okay, talking heads are, I don't know, is this better or worse? Laurent, Miklo, and I took this problem. Take the integers from 0 up to n and take simple random walk, and then reflecting at 0. If you hit 0 half the time, you stay, and half the time you go back. And if you hit n, you die, okay? That couldn't be a simpler problem. And it has a quasi-stationary distribution, which you can write down, and it's something like a piece of cosine. You know, it's an explicit function. It's big near 0, and then it goes down, and of course it's 0 at n. And we wanted to just get an honest rate of convergence of, you know, the Markov chain. You know, look at the Markov chain, given that it hasn't been absorbed up to time t, subtract off the quasi-stationary distribution, look at the total variation distance between those two. When is it small? And we know all the eigenvalues and all the eigenfunctions of this problem. And we're also, you know, brave, hardworking fellows, and we got n squared log n, and we couldn't get rid of the log n. I mean, and I know the answer is n squared in my heart, but I couldn't do it. And that's what comes out of this theorem. Okay, so even though I don't know what it seems like to you, I tried pretty hard in a situation where I could write everything down. And the analysis, there's not cancellation. You just can't bring the absolute values inside. It really was delicate, and we couldn't do it. We can do something, I mean, but we had an extra log, and this, and that's the simplest possible setting. So it's just, I'm impressed by this theorem, and it uses all of this geometric stuff, and I like it. I'll come back in a second. Okay, so so that's. Now let me do an example. That's what I said I was going to do. Let's talk about the 3 gamblers. Okay, you have all of this abstract theory. I have this very concrete problem. What does it say? So you remember, U was this triangular region where x1 was positive, x2 was positive. The boundary was this and this, and this was on the boundary, and x1 plus x2 is less than n, equal to n is on the boundary. So, and you know, the graph is, let's see, I have a picture of the graph someplace. There's the graph, right? The graph has these extra edges in it, stuff. I'll explain this graph in a second. So that's where we were. So one issue is, you know, what's beta naught? This is a very concrete problem. What's beta naught and what's phi naught? Well, in general, good luck to you. But in this example, we can do it. And why can we do it? It's because LeMay, you know, 1880, 1850, LeMay diagonalized Brownian motion. He didn't call it that. He diagonalized the Laplacian on a triangle. Okay, you can explicitly diagonalize the Laplacian on a triangle. If you can explicitly diagonalize the Laplacian on a triangle, I can do this. And so we did it. It's work, and let me just tell you the answer for a second. So first of all, so this is n. Beta naught, the Perron eigenfunction, is basically, you know, 1 minus a constant over n squared, but it's actually exactly equal to this. That's the theory says. Phi naught of x1, x2 on the triangle, you know, a miracle occurs. We can write it all down. You know, it's 2 over square root of 3n. This sign minus those two signs. Now, if you try to look at this, I promise you this is positive. I guess. I mean, it's not so easy to look at. You know, you could get Mathematica or something to draw a graph of it. What does it look like? Well, here's an approximation which I find useful. This approximation is uniform in x1 and x2, even up to the corners. Okay, so this is the quasi-stationary distribution for the Gambler's ruin problem. It's x1, x2, x1 times x2, the sum of the x's, and then it's n minus x1, n minus x2, n minus the sum of the x's. So these two things are uniform. When I use this double wiggle notation, it means that this and this are bounded uniformly in x1 and x2 above and below by each other, that there are two positive constants. So it's nice when you can do that. And in this case, we did it. So it's still, this is easier to look at. Everything in sight is positive, at least. It, you know, it vanishes on the boundary as it should. And let me just let you look at it with me for a second. So if you were in the middle of the triangle, that's what this means, phi naught of, you know, n over 4, something like that. This quasi-stationary distribution is around constant over n, and you can just see that, right? If this is n and this is n and these are n and all of these are n, you know, this is, you know, this is n to the 6th, you know, 1, 2, 3, 4, 5, 6 over n to the 7th, and it's around 1 over n. It goes to 0 as you go to the corners. How does it go to 0 as you go to the edges? Well, as you go to a corner, it vanishes as the cube of the distance to the corner. It's not easy to picture the quasi-stationary distribution in this problem, but this is it. Our theorem says that if t, the amount of time you run things, is bigger than, you know, a constant times n squared, then nu of t, the chance that the process is any place in the triangle, given that it's still alive, is proportional to this quasi-stationary distribution. So that's an example of the theorem in action, and you know, so you're away from the boundary, but exactly what the shape is, you know, it's. We wish we could do this with 4 gamblers, or we encourage one of you to try to do it with 4 gamblers or k gamblers. Let me go on. I want to get back to the Chris Ferguson's problem. I'm not going to go through it, but let me at least tell you, our paper, which is quite a long technical paper, has many other examples. The 3 gamblers is a separate paper. We actually broke it off and made a separate paper. But you can just take a rectangular box in the lattice in k dimensions. not necessarily a square, and A by B by C by D, something like that. That's another version of Gambler's Rune with many players. The story is there are two gamblers and there are K currencies, okay? And each time you pick a currency and then you flip a coin, and if it comes up heads, one pays the other in that currency, and if it comes up tails, the other way, and what happens. And in this problem, you can also explicitly diagonalize everything. But if you take a sphere or a metric sphere, an L1 sphere, or if you take a sphere and take a ball out, or if you take a convex set of lattice points and maybe remove a few points, the theory applies to all of that. We have the same kinds of understanding of the quasi-stationary distribution, pretty good hold on it. And in these problems, especially, we don't have formulas. Nobody has formulas for what the Perron eigenfunction is for these. We get our hands on the Perron eigenfunction. The eigenvalue is 1 minus constant over r squared. We get our hands on the Perron eigenfunction by using what are called Carleson estimates. And I was thinking about trying to do that, but it really is a separate talk. They're amazing deep theorems of Leonard Carleson, and I never appreciated them, and now I say, my God. And he, of course, did them in continuous domains and everything smooth, and we were saying, well, we're going to have to, you replace differentiability by differences and do whatever it is we do. And if you ever look, it's not exactly so simple. And what we realized is, at least for this part of the paper, if you look at the cable process, that is, look at Brownian motion on the edges of the graph, then it's continuous, and you can use the Carleson estimates, and then by a trick, you have to say how the Brownian, what the Walsh spider, for those of you who knew John, you have to say what happens when you hit a point. There's a parameter, and you can tune the parameter so that it exactly matches up. And what you want from the continuous problem for the discrete problem exactly matches the continuous problem. So that's a wonderful discovery, but it's a 30-page argument. And I've just told you whatever you would get if you saw the technicalities of it. So we didn't have to redo that part of analysis. So that's what I mean by Carleson estimates and cable processes to the rescue. I will give you a reference for all of this stuff in a minute. Okay, so I just have outlined a subject, which is rates of convergence of quasi-stationary to quasi-stationarity. I told you that for nice domains, in a rather specific sense, we could make progress, and I try to give you an indication of what the progress looks like. Let me say something bad about what we've done. Our notions of nice, we're using Nash inequalities and things like that, they're all low dimensional. If I want to do something on the permutation group or something on the hypercube with a growing number of dimensions, these techniques don't work. So this is intrinsically a low dimensional, works for 5 dimensions, it's fine. The constants depend on the dimension, on the growth of balls and things like that, and they're not good. We know what they are, and I would be lying to you if so this is it's a very general setup, but it's a low dimensional story. Okay, now I want to get back to harmonic measure. And I want to get back to Chris Ferguson's problem. So let me get back to it. So remember, harmonic measure is, I'm doing my random walk. I die when I hit the boundary. Here the boundary is this, this, and this. Okay, I'm doing my random walk. I die when I hit the boundary. Given where I started, X, what's the chance I die at some boundary point? That's what the question is, okay? And that'll be important for where we're going in a second. Now, this triangle problem, A, B, and C, it's a triangle, right? And so it's got a lot of symmetries in it. You know, A, B, and C aren't the same, but that's just where we are inside the triangle. And if you know the answer to this, so first of all, look at the first two coordinates. If you just need to know, if you start at one of these yellow points, what's the chance that you die on this? You can rotate everything. If you know how to do these, you can, you know, permute the variables and get what you want if you know the answer to this. So that's not hard to imagine, and it's true, and let me leave it at that. So this is x1 and x2 are both positive, and I think this is x1 is, let's see, x1 is less than or equal to twice x2, something like that. So you only have, I'm not going to pay attention to that, but just so that I don't lie in the statements that are about to come, I'm starting at one of the yellow points, and I only need to know what's the chance I wind up on this part of the boundary. And if you know how to do that, okay. So I'm going to call how far over we are here y. That's what it's called. And then x1 and x2 are where we start. So do this random walk. What's the chance that when we exit at one of these points? That's when we die at one of these points. That's what I'm going to tell you about. Okay, so we know this pretty well. We know it for you slightly more special than John domains. We know it for you what are called inner uniform domains. And let's see if I can stop my share and go back and get my picture here. Okay. No. Let's see. No, I don't want that. I don't. How about this one? That's it. Can you see this colored picture? No. Do you see carrots and bananas? These
We
guys?
see a colored picture.
Good. Okay. So this is my attempt to explain both John domains and fruit, if you like. So carrots and bananas. In a John domain, any point can be connected to a central point by a path which gets further and further away from the boundary as you move along the path. Okay, that's a John domain. An inner uniform domain, they are John domains, but they're much more restricted. Any pair of points can be connected by a path such that as you move along the path, you get further and further away until the middle, and when this point might be close to the boundary. So as you move along the path, you get further and further away from the boundary, and then you come back to that. So I could write down the definition. I don't think it'll help you as much as this picture. They're a more restricted class of domains, but I need those for the Carleson estimates. So I just told you about carrots and bananas. Okay. I don't need this anymore, so let me get rid of it. Well, I want to, screen sharing is stopped. The shared window is closed. That's okay with me. I want to start screen sharing again and help. Okay, I want to go to this picture. Sorry for my technological impairment, but okay, so we know pretty well about what the harmonic measure is for inner uniform domains, and I'll just tell you the result for 3 gamblers. Okay, I think in my efforts to be friendly, I'm going to do that. So here's the theorem, and then I'll try to let you look at it and think about it. But this is an example. And then I'll try to take it back to poker. So you start at x1 and x2 there among the yellow points. What's the chance that the first time that you die is at one of these blue points, y0? That chance is asymptotic to, in this funny sense, I wish it were better, upper and lower bounded by uniformly in x1 and x2 and y, uniformly, this funny function. Okay, so not so easy to look at. It's not so different from the first eigenfunction, but it's rather explicit, and I'll specialize it. But so it's the product of the x's, their sum, n minus the sum, n minus x2, y squared, n minus y squared in the top, n to the fourth, y plus d squared. What's d? D is the graph distance, and this is a funny graph. It's got these triangular edges in it. D is the graph distance from x1 and x2 to y. Okay, so the graph distance from x1 and x2 to y. That's what it is. So that's our Poisson kernel, and we killed ourselves I wish music could come on now, but that's the main content. So let me help you look at it for a second.
We can try to arrange for some music.
Please not. Suppose you start in the middle, okay? Suppose you somehow n over 3 to the middle. What's the chance that given, that you first exit the boundary, and here's why. Where do you exit? Well, you exit where you think you exit. You exit sort of toward the middle. That is, this thing is biggest in the middle. It's a product y times n minus y, but there's a square there. It's just not the first thing you'd think about. I don't know, at least not for me. And this is uniform in y. So you exit in the middle if you start in the middle. You exit in the middle of y. If you start in a corner, I'm starting here at 1, 1. Where do you die? Well, of course, you die close to here. And how does it fall off? It falls off as y to the fourth. And again, those aren't such easy exponents to guess at. I don't have any heuristic for guessing at that. But, if you like, take this n squared, put it here. That's 1 minus y squared. That just doesn't cause any trouble. And this is, 1 over y to the fourth. So it's how this falls off. And if x1 is big, and if x1 is 1 and x2 is almost everything, so the second player has almost all the money, so you're here, where do you die? Again, you die in the middle, but this is rarer. And this n to the sixth says, of course, it's most likely that you die over here, right? If you're here, so the chance that you die here, it's got an extra power of n down there compared to this n to the fifth. But other than that, so all of this and much else is hidden in this formula. Okay, so let me try to apply this formula to say something about the three gamblers and the permutations and stuff like that. So that's how I'm going to finish up. And finally, it says here, there are these 6 exit probabilities, right, that I said I was interested in. And x1 and x2, x1 is A, x2 is B, and C is n minus x1 minus x2. And I'm sorry, I'm going to use both notations. So what's the chance, given that you started at A and B, at x1 and x2, what's the chance that the first player that is eliminated is the one with x1, the second player that's eliminated is the one with x2, and the third player winds up with all the cash? Well, what that is you have to hit the boundary. You hit the boundary at some point y, and then we know you're just doing ordinary gambler's rune. And if you're on the edge, we know how gambler's rune goes, and that's n minus y over n is the chance of C winding up with all the money. So this formula, now this is a theorem that the chance of this permutation is given by this formula, okay? So let's look at it in a case or two. Suppose you start in the corner. So x1 and x2 each have $1, and the third player has all the money. So of course the chance that the third player, what's the chance that this is the chance that the third player is eliminated last, but it's A, B, C. So of course, A and B, it could be A, B, C, and it could be B, A, C, right? It could be first player's eliminated, or the second player's eliminated first. They're symmetric, right? So this should be about a half. What this approximation gives, and I'm just plugging into this formula, is it says it's a half. I won't take you through the calculus. It's a half. It's this charming formula, and you plug in one, and you calculate the distance and all of that, and it turns out it's that, and this is pretty close to 1. This is falling off. It's y to the 4th. This is pretty close to 1, and so this is close to a half times zeta to the 4th, and this goes away, and when n is large, and that's when this calculation puts this term in, and that's a little bit more than a half, which is off. But what's the chance that that finishing order, you started out the same way, 1, 1, n minus 2. What's the chance that the player B is left with all the money? Well, you can plug into that formula, and it comes out to be this, and that's something like 1 over 2n times zeta of 3. So to the takeaway, forget the zeta of 3, that's just a number. Of course, it's zeta of 3. It's a famous number, but this is rare. It's 1 over n. And of course, that's right. If one of the players has all the money, it's very unlikely that a player with $1 will finish out. But how does it go? It drops off as a function of n. So you see these powers of n coming in. Okay. One of the things, Stewie here is helping me with many things. One of the things that he's helping me with is you can get exact numbers if n is 100 using the computer, not Monte Carlo, using linear algebra. You can get exact numbers, and these numbers match exact numbers pretty well. I mean, when n is 120, we can do it in closed form. Let's do it in closed form. What's the chance that if player 1 has $1, player 2 has $1, and player 3 has the rest, that they finish in this order? Well, it's exactly a half times n minus 2 over n. Why is that? Well, the chance that player 3 winds up with all the money is n minus 2 over n, and it's symmetrical in players 1 and 2. So that's close to a half. It's 0.487. So this 0.511, it's not perfect. It's not very good, but it's not so far off. And similarly for other cases, that is when we compare. Now, my colleague Saloff-Coste, I think his hair stands on end when I'm doing this. These theorems, these double wiggles, they're pretty bad. They're not meant to be numerically accurate. They're asymptotic in n and here I'm trying to actually use them, but they're not so bad. So they give reasonable rates. There are 2 references. If you wanted to look more about this, there are 2 references. They're both papers with Kelsey, Houston Edwards, and Laurent. They're both on my webpage. They're both on the archive, soon to be a major motion picture. The first paper, which is the long paper that I talked about first, is Analytic Geometric Methods for Finite Markov Chains with Applications to Quasi-Stationarity. It's a hard paper. I taught a course last quarter, and I spent 3 weeks trying to do this paper for graduate students. I don't know if we were all speaking at the end of it, but it's a very well-written paper. We tried very hard. It's 110 pages long, and I'm sorry, I just try to give you a feeling for it. The Gambler's rune estimates and the general abstract version of estimating the Green's function, using the Green's function to estimate this harmonic measure. We did that in a separate paper, Gambler's rune estimates on finite inner uniform domains. Let me just tell you one thing okay. First of all, there are many things to do. Obviously, there are many things to do. For example, be nice to be able to solve Chris Ferguson's problem, to give some kind of way, if one guy has $100,000 and the other guy has $70,000 and the third guy has $1 million, how should they split up the money? What are the chances of the 6 orders? It doesn't seem like an unreasonable question. It's a reasonable question to give some way of getting approximations. Let me say, just so you know, I know, with 3 gamblers, you can do this. You can approximate, but first of all, you can map the simplex. You can approximate the thing by Brownian motion. You can always do that with any number of gamblers. It's a random walk. You can approximate it by Brownian motion on the simplex. And then you can map the simplex conformally into the circle. You know how to do that. And then you have a problem on the circle, and you can actually use classical analysis and do that problem. So actually, Chris's father, Tom Ferguson, did that, has a paper on the archive. And so that's a way of making some progress. Whether the approximation's useful and how different it is than our numbers, I don't know, but okay, you could try to do that. You can't do that in 4 dimensions, right? That is, sorry, I'll go back and stop my share. In 4 dimensions, you can approximate by Brownian motion, but we can't do the absorption time of Brownian motion in a simplex. I mean, we can't touch that problem. We know some things. Some of you may know this problem that Yuval Perez was selling for a long time, which is this cops and robbers problem. And this problem of absorption time is equivalent to the asymptotics of the cops and robber. You start with k minus 1 cops and 1 robber. The robber starts at 1. The cops do Brownian motion. The robber does Brownian motion. What's the chance that you ever catch the cops ever catch the robber? That's the same problem, more or less the same problem. People have studied, really, there are 30 papers. People have studied the Brownian approximation, and it's a problem of computing volumes in a certain cone. And for the cone, which is the triangle, we can compute the volumes. For the cone, which is a simplex, it's a 3-dimensional simplex bounding a sphere, we can't compute the volumes. And what we know is that, there were all of those powers of n I was talking about. All of those powers of n, they're not integers anymore. They're some funny numbers, and you can compute them to as many decimal places as you want, but you can't, they're the solutions of funny systems of equations, and you can't write them down in closed form. It's beautiful, beautiful math. Even doing 4 gamblers and getting the kind of approximations we get for 3 gamblers is for 4 gamblers would be a real achievement. There's a whole world that I haven't talked to you about, but there's a book about, we survey the literature in our papers. There's a nice book about quasi-stationarity, and in the paper I wrote with Laurent, we surveyed literature about quasi-station. People in genetics are interested in, creatures live and they die, and this quasi-stationary distributions, people are interested in them. As far as I know, there's been no work on quantitative convergence to quasi-stationary distribution, except the stuff I started with McLuhan and this. And there are a lot of interesting problems to try to do. I know that you gave me extra time, but I think that nobody can listen to me, charming and interesting as I am, for much more than of time I've gone. So let me thank you very much for your attention and surrender that talk I want to give.
Thank you.
Hi, Joel.
Hi, Persi.
Yes.
Yes. So questions or
at this point, we will stop the recording and we can have some questions as long as people wish to remain for either questions or socially.
Hello, everybody.